I'm Dave Franzen, Extension Soil Specialist, NDSU. This is 29th January in North Dakota, and I've probably spoken at this thing maybe 24, 25 times. So anyway, so I was asked by Lindsay Overmeyer if I would address soil compaction, and so I gave her that title, and you all read it. So let's get going. So review why this is an issue is that we started 2023, the season, the growing season, very wet, as you recall. Late spring, had a hard time getting in, and then, you know, the clock is ticking, and all the early crops are already late, and then the later crops, my God. So everybody's rush getting in the field, and I would have been the same way. And so usually after planting time, you get a shower of rain or something, and this year we got nothing, like for 3 months, something like that. That was it. And so what you had was spring compaction, which usually kind of heals itself. Later on in the season, it didn't get a chance. There were no wetting, drying. I'll show why that's important here in just a minute. But there you went. The last time this happened to me in my plot work was 2012, and I was working west of Fargo on some high clay soils, and the farmer went in. It was just like this. It was late. Wanted to get his corn in, put it in when it was wet, and usually you get, you know, half inch of rain, and that stuff heals up and acts like flour afterward. And nothing. Got nothing. And so the yields were half what they normally were. It was, you put a soil probe in the ground, it was like trying to go through concrete. So it was tough. So I get it. I understand why this is an issue. So we had spring compaction, and you had no relief. What I mean by no relief, I don't mean a bar. So normal aggregation, this is what you have. You know, nice pores, little creepy crawly things living in there, and what you had down a few inches was just this massive stuff. And I'm sure there was a little bit of crack, or you wouldn't have got any crop at all. But it certainly was a lot less nice of a growing medium than you normally have. All right. There's no math involved, so don't get too scared, but there is chemistry involved, because you have to understand a little bit about this to understand why it's important at all, why soil is important at all in this compaction thing, and what you might want to do about it. So you all have a general idea what clay feels like, right? Slick, stays wet for a long time. You can smooth it out in your hand. If you have any land judging experience, you can make a ribbon with it about that long. And that's, you know, so that's clay. So if you went to South Georgia, where they have a different chemistry of clay than what we have, in Pennsylvania, which has a different chemistry of clay than we have, and then up here, they'll all feel the same. The clays will all feel the same, but the chemistry would be vastly different, vastly different. So the building blocks of it, you might think that they're just little tiny particles, and the NRCS actually, if you go into their book and kind of look at particle size, it kind of makes you think that actually it's just the size that's important, but actually it's what makes up that size that's important. So the origin of our clays is up in Canada, in that some of the oldest rocks on Earth, the Canadian Shield, they call it, bunch of granite up in north. And granite is made up of feldspars, which are kind of the orangey kind of thing you see in granite, maybe. And then it also has mica in it, which is the shiny stuff. If you pick up a piece of granite, and I'm sure you all have some in your farms, you see a little shiny stuff in there, little sheets. That's mica. That's where the clays come from. That's where the clays come from. So mica is made up of these things. It's the precursor to the clays. And it's held together by a lot of potassium that smooshes the layers together, keeps them from coming apart. But as it weathers and weathers, it turns into hydrous micas, and it turns into smectites. And then it turns into kaolinites for just the gross period thing. So what are these sheets made of? These little black dots in the middle here is silicon, has a four positive charges, and it's surrounded by oxygen ions, and they form a tetrahedron. So this is four-sided, one side, two sides. Can't see the third side, and then there's a fourth side. And they form that particular tetrahedron, as my physical chemistry professor told the class one day. Somebody asked him a question, and he turned around, and the person asked, well, why did they do that? And he turns around and says, because they have to. So they form a tetrahedron because they have to, because that's just the way it is. That's just the way it is. So that's the silicon oxide sheet, and they bind together like this, where they're sharing electron clouds in this, think of a vast sheet of silicon oxide. That's what it is. So that's one of the sheets in a clay. The second sheet in a clay is aluminum ions, which are these orange ones in the middle here. That's one of them. But they bind together again. They're surrounded by OH ions, hydroxide ions, OH. Water is H2O. Take away the hydrogen and you got OH. That's where a pH and alkalinity, all that kind of stuff comes from. So in the fires of Mount Doom, where these things form, that's how they crystallize. Aluminum attracts the hydroxides, silicon attracts the oxygen, and then when they crystallize, once they get out of the magma and crystallize into the rock, then and into the mica, then they form these sheets because they have to. All right. So the really weathered stuff, the stuff you see in South Georgia, the stuff you see in Puerto Rico, the stuff you see in the southern part of the United States, where it's very, very wet and very, very warm to hot, is kaolinite. That's where a lot of the weathering has taken place, a lot of the destruction of the clay. The original mica has taken place, and so what you have is you have sheets of silicon bound to the OH ion. So what you have here is a partial negative charge with the oxygen, partial positive charge with the O, which is pointing this way. The hydrogen is pointing that way. So there's a positive charge, so like millions of these things in a very small area, binding together very, very tightly. No space in between those at all. That's kaolinite. And you have a little bit of it, but it's not important for you until you get out to Dickinson. What you deal with most of the time are these 2-to-1 sheets. They're mildly weathered to a little bit more moderately weathered mica, and they're the same structural sheets that mica has with some differences. But they have a sheet of silicon oxide, bound to the aluminum hydroxide in the middle here, and that's called a 2-to-1 sheet because these things act as one unit sheet all the way across. And then these things are stacked on top of each other with more or less space in between the 2-to-1 sheets, depending on how weathered it is. All right, so this is a depiction of what I just kind of showed you. So this is a nilite. So we have the 2-to-1. There is the silicon tetrahedral, the aluminum octahedral, and the silicon tetrahedral here. So you got one sheet of 2-to-1 clay, one sheet of 2-to-1 clay, a space in between, but just like the mica from which it came, it also has quite a bit of potassium in between these sheets that hold it very tightly. It can still crack, expand a little bit on the sheet ends, but not the whole sheet itself. Then you have the more weathered materials, like the Mount Marillanites, the smectites we call them. They're in the smectite class, biolites in there too. But they have the same 2-to-1 sheet, but because of the weathering, the potassium has more or less gone away. And so there's a lot more space in between so that water and certain cations can move in and out depending on how wet, how dry, how frozen, how not frozen the clay is. And these are the things that are important for you and the state in general, especially east of the river, that keeps you from having to deep chisel in between every crop. At least I hope to God that you don't do that. So if all of that is mud, if all of that is mud, this is what it looks like in real time. So these are kaolinites. They're bound one on top of the other. You can see that. You can see that here in this picture. The kaolinite, no space, crammed together. There's no shrinking, there's no swelling, there's no nothing. If you screw up and make compaction, you have to fix it because the soil ain't gonna do it for you. Those are what people in Dickinson have to deal with. And thank goodness they know what patience is, and so they don't have to do this very often. This is illite. You can see that it's still structured like the kaolinite is, but see the gaps in between where the potassium is oozed out and where the edges of the clay can kind of move in and out a little bit. More gaps there. So it's not quite as unforgiving as what the kaolinite is. But then look over here to a smectite or montmorillonite or bogline or whatever. And you got all this wavy stuff where there's space in between the sheets and it's moist. That's the difference. They feel the same, chemically very different. The way they act, the way they can heal themselves or not heal themselves, how you treat one compared to the other. So again, this is what you have with the 2-to-1. The 2-to-1, when you have the smectite clays, you have space in between, so water moves in and out as long as there's moisture. But when it dries, those collapse. There's hardly any water in there anymore. Traps any potassium. That's why potassium is our potassium recommendations for corn and some of the other crops, is because it collapses and it can't get out. Where if you have an illite, it's coated with, it's crammed full of potassium, and so it's releasing potassium. It doesn't care whether dry, but smectite does because it can collapse and trap it. This is the kaolinite, and it's just monolithic. Nothing moves in and out. And then the illite sheets resist water and movement in between. And so it's not nearly as forgiving as what the smectites are, where there's more. So this is in honor of Dwight Ockery. Brad's laughing. He knows what I'm talking about.
Where's your red?
I haven't known. Dwight Ockery is a wonderful ag economist. But regardless of how much we gently urged him not to put so much data on a slide, he still continued to put, like, I don't know, 100 lines of data on the slide, and then he tried to make people look at it. So anyway, so I went through, I think maybe you know that, gosh, how long's it been? 8-9 years ago, something like that. I went to every county in the state and pulled cores just from the surface 6 inches or so, sent them in from some ungodly rate to get the clay species and potassium feldspar content of all the soils. And so of course, I still have the data and I have where it comes from and everything, and all the soil series. So this is 6 sites in Ramsey County. There's 3 in Wells. There's 2 in Eddy, 1 in Western Walsh that I included. I didn't include the eastern stuff. It doesn't matter to you. Briggs County, Nelson County. So I have all of these for the most part, and until you get into the silty clays, the silty clay at the Parnell, which you have some up here, 35%. But most of these are light loams. You kind of live and die with your loam soils in this area. Around 20% clay. So 20% of all the mineral makeup of your soil is generally clay until you get into the sands, a mattock soil, and you can imagine where that comes from around mattock. Very, very sandy, and so you're down around 10%. And so really the clay chemistry doesn't really play as much of a role with those really sandy soils, and you're kind of on the brink right here. But you do have, depending on how much smectite you have relative to the rest, it can either be a help or not be a help. For example, this Heimdall, which is kind of the same kind of soil that they have in Carrington Research Center. is mostly illite. And so even though it has 20%, like this Barnes does, this site right here has more smectite, so it has more shrink and swell and it can heal itself, but this one I don't think would ever do that. You'd have to almost treat that place like it was almost a kaolinite. So there's a fair amount of smectite in most of your soils, but not all of them. This Hamerly from Ramsey County only has like 1% smectite, so it's not doing anything. Most of it is just illite with a little bit of kaolinite in there. So it's, if you screw that soil up, you're going to have to do something about it. All right, so that's an overview about what you're dealing with. Most of you are dealing with mostly smectite, some illite, a little bit of kaolinite. Yeah, the kaolinite because dust blows. You got that from the west. You didn't get it from here, but it drifted down, and so it's part of your soil now. Congratulations. All right, soils with dominant smectite will shrink and swell. People get all freaked out because it doesn't freeze or thaw. I don't get too excited about freeze and thaw because it especially at depth, it only happens once a year. You know, it freezes at depth and then it thaws at depth, and so you get one chance. But wetting and drying, that can happen several times during a year. And so that's really the biggest thing. Wetting and drying is more important, I think, than freezing and thawing. You got a really high clay soil, which is this. Trying to think where this was. Oh yeah. So it's actually, even though it's in the valley, it doesn't have that much more clay than what you have right here. And it has mostly smectite. So those few sites that had the illite as a dominant, it doesn't matter for this. But this is some work that Joe Giles did when he was working in Fargo, and he drove back and forth across these plots. And then looked at whether he just left it that way or whether he used a Piritil. Do you remember those things? I don't know if anybody uses those anymore. But anyway, it's kind of like a plow that doesn't stick its head above the ground, maybe. And then the straight shank's more like a chisel plow type thing. But it didn't matter what you did because you had one shrink and swell cycle in this soil, and it was perfectly fine. Okay, so I'll tell you a story about one of these sites. I think it was the Glendon site. So the Glendon site, he got halfway through all of that, and was driving back and forth, and then he got rained out. You know, half-inch rain, something like that, but they couldn't do anything. And so they came back a few days later, and just for fun, they went ahead and took a few cores into the place where they went back and forth across it, and it was just the same as where they didn't go back and forth at all. And I had the same experience west of Fargo several years ago, where the farmer thought it would be a really great idea to roll this field of sunflower last year. He had chiseled them, and then it was a little bit rough, and so he thought it would be a good idea to just run the roller across it. And I saw him run the roller. And if you can just imagine running a roller across chocolate pudding, that's kind of what it looked like when he was doing it. I thought, oh my God. So I came in a couple days later, and Norm Cadnock came in with a planter. You know, we're going to plant the corn across there. And you know, we had to do everything but jump on the back of the planter to get the dang thing in the ground. We even planted one of the plots twice because we couldn't even tell that we'd been in there. And then we got a half-inch of rain. I went back out there, and you could take your hand and you could just scoop it up. You just scoop it up with your hand. It was just one wetting and drying. That's all it took. And then all that power of water in between those clays, it just healed it. I don't expect that to happen to you because they have twice as much smectite as what you do. But that can happen if you have a few cycles. Just let you know. All right. So if you have soils without dominant smectite, or soils with less than 10% of their total mineral matter is smectite, which sands like that matic, patience is the virtue. And then I know because that's in short supply, especially with a year like this last one. Then think about the second one. Nothing you can really do for that year, but as you go into the next year, this is something you need to think about. Use of a shank strip till for row crops and rotation. Never dreamed in a million years when I came here in '94 the corn would be that popular here in this Devil's Lake area, but I know it is. Yeah, you have a lot of row crops up in this area that could use this. So this is what I mean. So this is the Maverick that Ken that Franzen has, and they've used it in their trials for a long time. And so I can't remember makes it as a getter. I think it is anyway. But it's just a shank. You know, something to cut the residue, and a couple of discs. They don't really turn the soil, but they just burn the soil up a little bit on the top of it. But the working part of this is that shank. This is a homemade system out by Center, North Dakota that I visited a number of years ago. And it just has this straight shanks. Just see how it goes in the ground. It's probably going in maybe eight inches, 10, you know, you can get it to maybe go 10 if you wanted to. And then the discs in the back are just to pile the soil behind it to make a berm. This is what it looks like in a really high clay soil down the southeast part of North Dakota. I think that field went 200 and some bushels an acre, and my end rate plots were in there. The highest end rate plot was 250 bushels, something like that. I mean, you can really pump out the corn with this thing. If you're thinking about no-till with corn, forget it. You know, this is really going to gain yourself 20 bushels an acre if you go the strip till. Because corn is a Mesoamerican crop, you know, from central Mexico. It doesn't like cold. It has a seed coat, but it's not that kind of coat. And so it likes to have things warm and likes to have things dry. And when you do this, you bear up the soil so it warms just the same as if you would work the whole dang field. And it also dries it out, just like a whole dang field. But then you have this stuff in the middle where you're keeping the biology and you're keeping your end credit, you're keeping your benefits of having it. And all you're doing is cracking the soil, and that's all you need to do. You don't have to turn the soil over when you have smectites or kaolinites. You just need to crack it enough so that the roots can get it through those cracks. That's all you need to do. This costs money. That not so much. It's only January. All right. So this is what it looks underneath. Emerson, who had these made in Illinois, was making these slides to show people where the ammonia can go or where the fertilizer can go. But what you're looking at is your shank comes down. You can either put the fertilizer down or you don't need to put the fertilizer down. It's completely up to you. And then those discs on the side are just making the berm. And between there and the spring, the berm will come down to almost level, but not maybe quite. And then you plant directly into that. You have a little residue cleaner on the front of it, just to make sure that the spare, the stray straw and that kind of thing is moved out of the way, so that you don't have the hairpinning. And you plant right into it. That's how it works. And it's cracked, but all of this aggregation in between these rows is completely intact so that the microbes can be working on your behalf. And the water can move into the soil as you have. The worst alternative there is use these deep rippers. I suppose it's a lot of fun to put grandpa in a big ass, you know, whatever the biggest tractor that John Deere makes and say, go for it. But it destroys all natural aggregation. It brings your salts and carbonates to the surface. That soil is going to settle from fall to spring and seal things up. And in the meantime, in the fall, it acts like a sponge. And so in some years, fields that have these things worked on are the wettest ones. All right, so a couple things about compaction. I'm going back to my Vern Hoffman roots on this. See, I'm evoking all these old people, you know, but I'm really old too, and so I can do that. So Vern Hoffman fans, you know, they're people remember Vern Hoffman, ag engineer, and so his mantra always was when people ask him, well, what's the pressure from the tires, and it's whatever the tire pressure is. That's what it is. But that's generally true if you have a flat across tread like that. So that it's more or less evenly distributed like this is. But on this tire here, it's rounded, this rounded tire. And so you have more pressure down and it's more pressure out. So if you're trying to minimize compaction, having the pressure spread over more ground and using lower tire pressure, that's going to be your friend when it comes to avoiding compaction. What do the pores look like? This is from a clay soil in Finland, but not that far away. You just get on a jet and you're there in a day. So these are 3D images in the macropore system in a non-compacted soil over here on the left. And this is the right from some experimental plots I had where heavy machinery drove over the ground in an experiment 29 years ago. And I'm going to bet anything that's an illite type of a clay. So it has to be cracked. You can get the soil too fluffy. Some people experience this. You have fluffy soil syndrome. You can get the soil so fluffy, let's say that you use, God forbid, you use the deep chisel in the fall and then it didn't rain and then you go into the spring and you got all this stuff. There has to be some compaction. You ever wonder what a press wheel's for? What's a press wheel for? Is to compact the soil around the seed so it draws the water up to the seed. There has to be, and if you don't have that soil to seed contact with a fluffy seed syndrome, then you get problems. All right, I don't want to talk about that. And the other problem is about working stuff. Let's say that, you've tried to go no-till for a few years, and then you have this spring, and you have all this compaction, and so what's the alternative? Well, the alternative is to do this. And I don't think that this is a good idea. You already lost 2 feet of soil. Do you really want to lose any more? And so I hope that as you go on, as God is my witness, I will never let my soil blow again. That's paraphrase, remember? She says, she's starving to death and she says, God is my witness, I'll never go hungry again. But anyway, I stole it from it. That's what the going thing. Anyway, so I hope I don't go to court about that. So that's my contact information. So I think we're probably done. But okay, in the back.
What are your feelings on COVID?
Yeah, so all right, so at least one of the companies that has the coulter thing, and by coulters I mean instead of making that pass with the one shank, they're actually, the coulters are going in the ground several inches. They're mixing all the soil up within that 7 to 10 inch area, and so it's mixing that all up. To me, that's a step in the right direction, but it's probably not the way that you want to end up. It makes feel, why is this happening all of a sudden? It makes people feel comfortable that have never been reduced till anymore, and it does keep a lot of residue around when you do that. If you have 30-inch rows, let's say, and the folders are digging up about 10 inches, there's still 20 inches of residue in between it, and so you're really going to stop the wind blowing with it, but you're not really helping the biology because you're going too deep. You're just destroying all of that. And so as far as a compaction helper, it doesn't do that at all. The shank going to depth is the thing that's really going to crack it and help you with it. It'll make you feel like you've really done something really good in most years, but I don't think in a year like this last year that it's really going to be much of a help to get in underneath whatever the compaction problem is. So it's in my second set of favorites. I really like the shank. Yes, sorry. Yeah, so the colder style strip tillers, and I'm not going to name names or anything. Again, it's a good, but people can make some big mistakes with it too. One farmer called me this spring and say that it was really dry. It was really dry this spring, going in, and so I thought I'd just go back in with the strip tiller and freshen it up. And he dried it out, and the beads never came up. I mean, oh, what the heck he did. But again, you can just, well, I suppose in that case, you just got it too fluffy, dried it out to the depth of, nobody, I can't imagine why you did that. I said, why don't you call me before you did that? Well, I just didn't think about it. So anyway, it's not my favorite, but it's not a bad thing. They're outrageously expensive, in my opinion, but that's just my opinion. I don't own a $500,000 combine either. And I know people need them, so. Yes, sir.
Have you done a comparison between the track tire action?
Yeah, so the question was, we've done work with tires and tracks. And so Vern Hoffman used to tick people off all the time and say there's no difference between the two. That was 15 years ago or something like that. I don't know anybody that's done it since then. Yeah.
How do you determine if you've got LA spec type soil, clay in our soil?
Yeah, so we have a general map of smectite-like clays in the state. It's in our. I actually have a circular that's on my website, and it's on the extension publication pages about clay chemistry and its relationship to potassium and to tillage. And so those maps kind of give you a general idea of what the kind of clue it is. If you really want to know, then there's a laboratory up in Ontario that I could give anybody the address for. You go through their import-export part of it, because the people at the border freak out when you send soils up to them. I guess it's okay if you send 100 tons of sediment up the Red River every day. If you try to put a pound of soil in a box and send it to Ontario, then it's an international incident. But so anyway, it costs around $400 a shot. Yeah, so it's not a normal soil test. It has some really unique instrumentation and dedicated person to do it, and I don't think that they're making money hand over fist by charging even that much. Tried to get our XRD thing retrofitted at NDSU, sunk 20,000 into it, but just didn't have enough stimulations, enough sparks coming off of it to give us anything that we could really use. So it didn't work.